All right, so I want to talk about the continuity equation, which is the mass conservation equation for a fluid, for a continuum. And remember the general form of the conservation law that we got down in the previous lecture. If we have a quantity Q, then the conservation law is dQ dt plus div dot of the current of the quantity Q is zero. Zero if there's no sources or sinks. So if quantity Q is really conserved, sources and sources or sinks, then the form of the conservation equation is like this. And so we want to write down this equation specifically for mass conservation. So Q is the quantity per unit volume, and so for mass, Q is going to be the mass per unit volume, and that's the density. And we use rho, the Greek letter rho. And then we need also what the flux is going to be. So the movement of mass is going to be the velocity times the mass, right? The velocity of the mass times the mass. And so J of Q is going to be the velocity times mass, delta M, over delta V, right? Because we do everything, the mass flux per unit volume. And delta M over delta V, that's just rho. So this becomes just V vector rho. And so if we plug those into the general conservation equation, we get d rho dt plus div dot V rho equals 0. And so this is the continuity equation. This is the continuity equation. And it's also the mass conservation equation. Mass conservation. And you can think of it as being a budget for the mass for a fixed volume. So for a fixed volume, or volume fixed in space. Volume fixed in space. So that the volume fixed in space, we call that the Eulerian framework. So Eulerian. And we're going to contrast this to a conservation equation from a Lagrangian point of view, where now the volume is not fixed in space, but we take a finite amount of mass and we let that volume move around. So in this case, the volume is fixed, is defined, and we do a mass budget for that volume. For the Eulerian framework, for the Lagrangian, we take a fixed amount of material and we let it move with the flow, and then that volume will deform and change, but it will always contain the same amount of mass, right? So it's a volume following the motion of the mass particles inside the parcel, the Lagrangian one. So we want to contrast the two. So if what I want to get is an equation for the Lagrangian one, and if you remember the total derivative, right, following the motion, d by dt, right, that is just partial t plus v dotted with the gradient, right? Remember that was an exercise in the homework yet to derive this material derivative, or derivative following the motion. We want to apply this to the density. So I'm going to first start with this equation, the conservation equation, and then I'm going to use this and write down and obtain a Lagrangian mass conservation. So from this equation, d rho dt, right, plus, and now I'm just going to use the product rule on this quantity. So that'll be, right, I have the product of v and rho, so it'll be v dot with grad rho plus, and then the other one is rho div dot v. That's equal to 0. Right, so I've just expanded out this term, and then now you'll notice that this part here, right, d rho dt plus v div dot v dot grad rho is the same thing as d by dt of rho, right? So if I apply this to rho, in particular d by dt of rho is equal to d rho dt plus v dot grad rho. And so now I could substitute in here, and I get d rho dt is equal to minus, right? I'm left with this term, which I can bring on the other side, rho div dot v. And this one is also the mass conservation, but from a Lagrangian point of view. So this is mass conservation following the mass, or the material, I'll say, following the material. And that's the Lagrangian view. So here you can see that the way that if you're following the motion, d rho dt, is going to change if there is a divergence of the velocity. So in other words, if the velocity is being convergent at a place, then the density will go up, right? And because there's mass conservation, so if all the particles were to crunch in together, then the density would go up. That would be an example of mass conservation. Or if the fluid moves around and the velocity is divergent, right, then the things move apart. Div dot v is going to be positive, right, because there's a net divergence. With the minus, then rho will go down, right? So you'll get a divergence. So two different ways of thinking about mass conservation. One is for a fixed volume in space, called the continuity equation in Eulerian, and the other one is the Lagrangian point of view, where you follow the mass.